Picture three suns caught in a gravitational tug of war, each one pulling on the other two with no fixed center, no repeating pattern, and no way to say with certainty where any of them will be a million years from now. This is the three-body problem, and for more than 3 centuries it has stood as one of the most humbling puzzles in all of physics. It is not humbling because nobody has tried to solve it. Some of the sharpest minds in history have thrown themselves at it, armed with calculus, with mainframes, with supercomputers the size of warehouses, and every single one of them eventually ran into the same wall. The system does not just resist an exact solution, it actively destroys the ability to predict itself over long stretches of time. No matter how precise your starting measurements are, that destruction of predictability, not the difficulty of the arithmetic, is the real heart of the mystery. And it is why a strange new tool from the world of quantum physics has scientists rethinking what it even means to solve a problem like this. Before we get to qubits and superposition, it helps to sit with just how strange the three-body problem really is. Because the strangeness is the whole reason quantum computing entered the conversation in the first place. Isaac Newton gave humanity the law of gravity in the late 17th century, and with two bodies, say a planet and a star, his equations work beautifully. You can predict an eclipse centuries in advance, chart a comet's return down to the day, and send a spacecraft to a precise rendezvous point using nothing more exotic than Newtonian mechanics refined over the generations. Two bodies orbiting a common center of mass trace out clean, repeating ellipses forever, locked in a rhythm as steady as a heartbeat. Add a third body of comparable mass into that same gravitational dance, and something remarkable happens. The clean ellipses break apart. The system no longer settles into a repeating pattern. Instead, the three objects tug on each other in a constantly shifting arrangement that can loop, swing, eject one member entirely, or fall into brief pockets of near stability before spiraling back into disorder. The mathematician Henri Poincare stumbled into the deepest implication of this back in the 1890s, while trying to win a prize offered by the King of Sweden for anyone who could prove the solar system was stable. Poincare initially submitted a paper claiming a kind of qualified success. But when an editor found an error in his reasoning while preparing the work for publication, Poincare discovered something far more important than the mistake itself. He realized that even tiny, seemingly insignificant differences in the starting positions and velocities of three gravitating bodies could snowball over time into wildly different outcomes, to nearly identical starting configurations, differing perhaps by a distance smaller than the width of a human hair when scaled to a solar system, could diverge after enough time into completely different fates. One version of the system might settle into a long-lived, wobbling but bounded configuration, while the other could see one star flung out into interstellar space entirely. This sensitivity to initial conditions is now recognized as one of the founding observations of chaos theory. And it means the three-body problem is not merely hard. It is fundamentally unpredictable beyond a certain time horizon, no matter how good your equipment gets. This is worth pausing on, because it is easy to assume that unpredictability just means we need better computers, more decimal places, faster processors. That assumption turns out to be wrong in a very specific and fascinating way. If you take a modern supercomputer, one capable of billions of calculations every second, and ask it to simulate three gravitationally interacting stars far into the future, the simulation will produce a very precise, very confident-looking trajectory. The problem is that this trajectory is only as good as the tiny sliver of a second, where rounding happens inside the machine's memory. Computers cannot store infinitely precise numbers. At some point, every number gets truncated or rounded to fit within a fixed number of digits. And in most physical systems, that tiny rounding error stays tiny, contributing an error so small it never matters. In a chaotic three-body system, that same tiny rounding error grows. It does not grow slowly, unpredictably either. It grows exponentially, doubling and redoubling with every simulated orbit, until what began as an error smaller than the width of an atom eventually swamps the entire simulation and renders the long-term prediction meaningless. Physicists gave this exponential blow-up a name borrowed from a Russian mathematician named Alexander Lyapunov, calling the time it takes for small errors to overwhelm a prediction the Lyapunov time. For chaotic three-body systems, the Lyapunov time can be shockingly short on astronomical scales, sometimes just a handful of orbital periods. If you are enjoying this journey into the strange edge, where physics meets computation, take a moment to think about which topic you would want explored next in this kind of depth, because the questions this series tries to answer usually come from exactly that kind of curiosity. So, classical computers, no matter how fast, hit a wall that is not really about speed at all. It is about the mathematics of chaos itself, refusing to let long-term predictions hold together. This is where quantum computing enters the story, not as a magic wand that erases chaos, but as a fundamentally different way of representing and processing information that some researchers believe could offer real advantages for certain classes of these problems. To understand why, it helps to strip away the mystique and look at what a quantum computer actually does differently from the laptop or phone you are using right now. A conventional computer, no matter how powerful, stores and processes information using bits, and each bit is either a 0 or a 1. Every calculation your computer performs, from rendering a video to running a physics simulation, ultimately reduces to enormous numbers of these 0 or 1 operations happening at tremendous speed. A quantum computer instead uses quantum bits, usually called qubits, and a qubit can exist in a mixture of the 0 state and the 1 state simultaneously, a property known as superposition. This does not mean the qubit is secretly 0 or secretly 1, and we just do not know which. It genuinely occupies a combination of both possibilities until it is measured, at which point it collapses into one definite outcome. When you link many qubits together, the number of these simultaneous possibilities grows exponentially. 2 qubits can represent a superposition across 4 combined states at once. 10 qubits can represent a superposition across roughly 1,000 combined states at once. This exponential growth is the source of quantum computing's theoretical power, and it is also the source of a great deal of hype that outpaces what today's hardware can actually deliver. It is important to be precise here, because this is exactly the point where popular science coverage often drifts into exaggeration. Superposition does not let a quantum computer simply try every possible answer at once and hand you the correct one. The way a common misconception suggests, quantum algorithms work by carefully engineering interference between all those simultaneous possibilities, amplifying the probability of landing on useful answers while cancelling out the probability of landing on useless ones. Designing an algorithm that achieves this amplification for a specific problem is extraordinarily difficult, and only a handful of problems have known quantum algorithms that provide a proven speed advantage over the best classical methods. Simulating physical systems, particularly quantum mechanical ones, is one of the areas where theoretical physicists have long suspected quantum computers could shine. An idea traced back to the physicist Richard Feynman, who argued in the early 1980s that nature itself runs on quantum rules, so a computer built from those same quantum rules should, in principle, be far better suited to simulating nature than a classical machine built from ordinary bits. Gravitational dynamics like the three-body problems are not quantum mechanical in the traditional sense. Stars and planets are enormous, classical, everyday objects governed by Newtonian and, in more extreme cases, Einsteinian gravity, not by the quantum rules that govern electrons and photons. So why would anyone think a quantum computer could help simulate something as thoroughly classical as three stars orbiting each other? The answer lies not in the physics of gravity itself, but in the mathematics of the differential equations that describe it. Researchers in a growing field sometimes, called quantum simulation of classical dynamics, have been exploring whether certain classical chaotic systems, including simplified versions of orbital mechanics, can be reformulated in a mathematical language that a quantum computer can process efficiently. Even though the underlying physics being simulated is not quantum at all. This is a genuinely active and legitimate area of research, but it remains largely theoretical and experimental, confined mostly to small-scale proof-of-concept demonstrations rather than practical, large-scale astrophysical forecasting. To understand what current quantum hardware can and cannot do, it helps to look at the two broad approaches researchers use when they talk about quantum computers: tackling optimization and simulation problems. The first approach uses what are called gate-based quantum computers, which manipulate qubits through sequences of precise quantum logic operations, somewhat analogous to how classical logic gates manipulate bits, though the underlying rules are governed by quantum mechanics rather than classical logic. Companies and research institutions building gate-based machines have steadily increased the number of qubits available, moving from a handful of qubits in early prototypes to devices boasting well over 1,000 physical qubits in some of the more advanced systems unveiled in the mid-2020s. The second approach uses what is called quantum annealing, a specialized technique that does not attempt general-purpose quantum computation, but instead is purpose-built to search for low-energy or optimal solutions to certain types of mathematical optimization problems by letting a system of qubits settle naturally into a low-energy configuration that represents a good answer. Both approaches face a shared and stubborn obstacle known as decoherence. Qubits are extraordinarily fragile. The delicate superposition and entanglement that give quantum computers their theoretical power can be disrupted by the faintest interference from heat, electromagnetic noise, or even cosmic rays passing through the hardware, causing the qubits to lose their quantum information and collapse into ordinary classical bits before a calculation finishes. This is why many quantum computers are housed in refrigeration, systems that cool their processors to temperatures colder than deep space, often within a fraction of a degree of absolute zero, in an effort to shield the fragile qubits from thermal noise long enough to complete useful calculations. Even with this extreme cooling, most of today's quantum processors can only maintain reliable quantum information for a very brief window of time, measured in millionths of a second, before errors creep in and the calculation's accuracy degrades. Engineers refer to the current era of quantum computing as the noisy intermediate-scale quantum era, a deliberately modest label that reflects the honest state of the technology, powerful enough for meaningful experiments, but not yet powerful enough or clean enough to reliably outperform classical supercomputers on most real-world problems. With that honest picture of the hardware in mind, we can return to the three-body problem and ask a more careful question than simply whether quantum computers have solved it. The more accurate question is this: could a quantum computer, even a small, noisy, present-day quantum computer, offer any genuine insight into chaotic gravitational systems that classical machines struggle to provide? A number of physicists and computer scientists have explored this question from several angles, and the honest answer is nuanced. There is no dramatic headline moment where a quantum processor definitively cracked the three-body problem. The way a locksmith might crack a safe. What exists instead is a slow, careful, and genuinely exciting body of research, exploring whether quantum algorithms can represent chaotic dynamical systems more efficiently, whether quantum annealers can help identify stable orbital configurations hidden inside otherwise chaotic parameter spaces, and whether the peculiar mathematics of quantum interference might reveal patterns in orbital stability that classical numerical integration tends to miss because it processes one trajectory at a time. One promising thread of this research involves reformulating orbital mechanics problems as optimization problems, then applying quantum annealing or variational quantum algorithms to search for stable or quasi-stable configurations. Think of it less like predicting a single, definite future for three specific stars and more like mapping out an entire landscape of possible outcomes, searching for valleys of relative stability nestled within a much larger terrain of chaos. Classical computers can do this kind of landscape mapping too, and for smaller systems, they often do it perfectly well. The theoretical hope surrounding quantum approaches is that, as the complexity of the system grows, involving more bodies, more variables, or finer resolution across the parameter space, a properly designed quantum algorithm might scale more gracefully than the classical alternative. This is sometimes called a quantum advantage, and it remains, for gravitational chaos specifically, an open and actively debated question rather than a settled achievement. Researchers have demonstrated small-scale quantum simulations of simplified chaotic systems on hardware with only a few dozen qubits, useful as proof-of-concept work and genuinely valuable for developing the underlying algorithms. But these demonstrations are a long way from the kind of full-scale, high-fidelity stellar dynamics simulation that popular headlines sometimes suggest already exists. It is worth taking a detour here to talk about entanglement, because it plays a genuinely important, if often misunderstood, role in how physicists think about representing multi-body systems on quantum hardware. Entanglement is the phenomenon where two or more qubits become linked in such a way that the quantum state of one cannot be fully described without referencing the others, even if those qubits are physically separated. Albert Einstein famously distrusted this implication of quantum mechanics, referring to it in a 1935 paper co-written with Boris Podolsky and Nathan Rosen as involving what he considered troubling, almost paradoxical correlations. And in later personal correspondence, he expressed skepticism about entangled particles influencing each other over distance, a notion that entered popular science writing as spooky action at a distance. Decades of rigorous experimental tests, including increasingly sophisticated versions of a test devised by the physicist John Stuart Bell in the 1960s, have since confirmed that entanglement is real, rarefied, and now a foundational resource used deliberately in quantum computing, quantum cryptography, and quantum communication research. When researchers talk about entangling qubits to represent a three-body gravitational system, they are exploring whether the correlations between the positions, velocities, and gravitational influences of the three bodies can be encoded directly into the entangled relationships between qubits, rather than being calculated separately and then combined afterward the way a classical computer must do it step by step. In principle, this could allow certain relational properties of the system, such as how sensitive the whole configuration is to a small perturbation in just one body, to be extracted more directly from the quantum state itself. This is an elegant theoretical idea, and small experimental demonstrations of encoding coupled oscillator systems, which share some mathematical similarities with orbital dynamics, into entangled qubit states have been published in physics journals over the past several years. It remains, however, a research frontier rather than an operational technology, and claims that this technique has already been used to reliably forecast the long-term fate of a real, well-known multi-star system go well beyond what the published science currently supports since Alpha Centauri came up. It deserves a closer and more careful look, because it makes a wonderful case study in exactly how nuanced real orbital dynamics can be. Alpha Centauri is not, strictly speaking, a chaotic three-body puzzle waiting to be cracked. It is a hierarchical system, meaning it is better understood as a close, gravitationally bound pair, Alpha Centauri A and Alpha Centauri B, orbiting each other in a relatively well-behaved, well-characterized elliptical dance with a period of about 80 years, while a much smaller and more distant red dwarf star, Proxima Centauri, orbits that inner pair at a vastly greater distance, completing a single circuit only after many hundreds of thousands of years, based on the most recent orbital solutions derived from precise astrometric data gathered by space observatories, designed to measure stellar positions with extraordinary accuracy. Because the separation between the close pair and the distant third star is so large compared to the separation within the pair itself, the system behaves, to an excellent approximation, like two separate two-body problems rather than one fully chaotic three-body problem. This kind of hierarchical arrangement is actually the most common way nature resolves the instability inherent in multi-star systems. Truly chaotic, tightly packed triple-star systems with comparable masses and comparable separations do exist in the universe, but they tend to be short-lived on astronomical timescales, because that very instability we discussed earlier eventually ejects one member or drives a collision, leaving behind either a stable hierarchical arrangement like Alpha Centauri or a simpler surviving pair. This observation that nature itself seems to filter out the most chaotic multi-star configurations over time is one of the genuinely fascinating results to emerge from decades of careful astronomical surveying and computer modeling. Long before quantum computers were part of the conversation, astronomers have used classical numerical simulations, refined continuously since the earliest computerized orbital integrations, run by pioneering researchers such as Sver Arsith starting in the 1960s, to catalog how frequently triple and higher-order star systems form, how long they typically remain in unstable configurations, and what fraction eventually settle into long-lived hierarchical arrangements. These classical simulation codes, refined and accelerated over half a century of steady computational progress, remain the workhorse tools of modern stellar dynamics research, and they continue to produce robust, well-tested, peer-reviewed results about how star systems evolve, entirely independent of whatever progress quantum computing eventually makes. Interestingly, one of the most genuinely exciting recent developments in speeding up three-body predictions did not come from quantum computing at all, but from an entirely different branch of computer science, machine learning. A research team publishing their results in the astrophysical literature toward the end of the 2010s trained a deep neural network on a large library of classically simulated three-body trajectories, then asked the trained network to predict the outcome of new three-body configurations it had never seen before. The result was striking. The neural network could produce predictions many orders of magnitude faster than a traditional numerical integrator, while maintaining reasonable statistical accuracy for classifying the eventual, longer-term fate of the system, such as which body was most likely to eventually be ejected. This is a wonderful reminder that computational breakthroughs in chaotic dynamics research have been coming from multiple directions at once. Classical numerical methods, artificial intelligence, and machine learning, and quantum computing among them, each contributing its own strengths, rather than any single technology delivering a singular, dramatic solution to the whole problem. This brings us to another place where enthusiasm sometimes outruns the evidence. The idea that quantum computers are currently being used to plot navigation routes for deep space probes, traveling through regions with multiple gravitating stars. Real spacecraft navigation, including some of the most celebrated feats in the history of space exploration, relies overwhelmingly on classical computation, refined trajectory design techniques, and decades of accumulated engineering practice rather than quantum hardware. When engineers designed the gravity assist maneuvers that sent the Voyager probes past Jupiter, Saturn, Uranus, and Neptune in a single elegant tour made possible by a rare planetary alignment, they used classical Newtonian mechanics computed on the room-sized mainframes of the 1970s, later refined with more modern classical computing tools. As the mission progressed across the following decades, when mission designers plotted the intricate, fuel-efficient trajectories that carried the Cassini spacecraft through more than a decade of orbital maneuvers around Saturn and its moons, they relied on a mathematical framework built around something called invariant manifolds, essentially mapping out the natural pathways carved through space by the combined gravity of multiple bodies, a technique developed within classical dynamical systems theory that itself borrows deeply from the same chaos theory concepts that Poincare pioneered while studying the three-body problem more than a century earlier. None of this is meant to suggest that quantum computing is irrelevant to space science or to gravitational physics broadly. It simply means the genuine, verified applications of quantum computing today lie in somewhat different territory than plotting star charts. And understanding where quantum computers are actually delivering results helps calibrate expectations for where the technology might realistically go next. Quantum computers have shown measurable, published advantages in simulating the behavior of small molecules and chemical reactions, a task that scales so poorly on classical computers that even modest molecules quickly become intractable to simulate with full quantum mechanical accuracy, because the number of quantum states needed to describe a molecule's electrons grows exponentially with the number of electrons involved. Pharmaceutical researchers and materials scientists view this as one of the most promising near-term applications of quantum hardware, since a quantum computer built from qubits is, in Feynman's original sense, simulating quantum systems using quantum systems, a natural fit rather than an awkward translation. Quantum computers have also demonstrated genuine, carefully verified advantages on narrowly defined mathematical benchmark problems, specifically designed to showcase quantum speed, most famously in a landmark demonstration published in the scientific literature toward the end of 2019. In which a quantum processor completed a highly specialized sampling task in a matter of minutes that researchers estimated would take one of the world's most powerful classical supercomputers thousands of years to replicate using the most efficient known classical algorithms at the time. Critics and other research groups quickly pointed out, in the normal and healthy back and forth of scientific debate, that this particular benchmark task had no direct practical application and that improved classical algorithms later narrowed the gap considerably. But the demonstration remains an important milestone showing that quantum hardware can, under the right carefully engineered conditions, do something a classical computer genuinely struggles to replicate, translating that kind of narrowly defined advantage into broadly useful advantages for messy, real-world problems like chaotic gravitational dynamics remains one of the central open challenges facing the entire field. Optimization is another area where quantum annealers and gate-based quantum algorithms have shown real, if still modest and carefully qualified, promise. And this is actually the category of problem most closely related to the chaotic stability questions we have been discussing. Logistics companies have experimented with quantum annealing hardware to optimize delivery routes and scheduling problems. Financial institutions have tested quantum algorithms for portfolio optimization. And materials scientists have explored quantum approaches to finding low-energy molecular configurations. In every one of these cases, the honest scientific consensus, reflected in peer-reviewed benchmarking studies, is that quantum hardware today performs comparably to, and sometimes worse than, the best classical optimization algorithms for most problem sizes currently accessible. Though researchers remain optimistic that as qubit counts grow and error rates fall, a genuine crossover point favoring quantum approaches will eventually emerge for some subset of these problems. Stability analysis in chaotic three-body systems is, at its core, a search through a vast space of possible configurations for the relatively rare pockets of long-term stability, which is precisely the kind of search and optimization task where quantum algorithms are theorized to hold long-term promise, even though the practical demonstrations remain, as of the most recent published research, confined to small, simplified test cases rather than full astrophysical scale problems. There is also a more subtle and genuinely fascinating theoretical connection between quantum mechanics and chaos theory that deserves mention, because it deepens rather than merely qualifies the story. Physicists have long studied a field called quantum chaos, which does not refer to running chaotic classical systems on quantum hardware, but rather investigates what happens to quantum mechanical systems whose classical counterparts would be chaotic. It turns out that quantum mechanics, with its inherent uncertainty and its refusal to allow a system to have perfectly defined position and momentum simultaneously, smooths out some of the extreme sensitivity to initial conditions that plagues classical chaotic systems, at least at very small quantum mechanical scales. This has led some theoretical physicists to speculate about deep, still not fully understood connections between the mathematics governing quantum uncertainty and the mathematics governing classical chaos, connections that trace back to shared mathematical structures first explored by physicists studying billiard ball models, and energy level statistics in complex quantum systems during the latter half of the 20th century. Whether these deep mathematical parallels between quantum uncertainty and classical chaos can be harnessed practically to help simulate chaotic gravitational systems more efficiently remains an open and genuinely unresolved question actively pursued by researchers working at the intersection of these two fields. Let us turn now to the question of dark matter and early universe structure, since the outline for this exploration gestures toward that connection, and it is worth handling carefully, because this is exactly the kind of speculative leap where science communication has to be especially honest about the difference between an established result and a hopeful extrapolation. Dark matter, the mysterious substance inferred from its gravitational effects on galaxies and galaxy clusters despite emitting no detectable light of its own, interacts with ordinary matter primarily, and perhaps exclusively, through gravity, which means that understanding how dark matter clumps and moves under its own gravitational influence is fundamentally an n-body problem, just one involving astronomically larger numbers of interacting particles than three. Cosmologists studying the large-scale structure of the universe, the vast cosmic web of galaxy filaments and voids that emerge from the early universe's nearly uniform distribution of matter, rely on enormous classical n-body simulations, some tracking the gravitational interactions of many billions of simulated particles across cosmic time, run on the largest classical supercomputing clusters in the world. Projects that have consumed months of dedicated supercomputer time and represents some of the largest classical computing efforts ever undertaken in physics. If quantum computing eventually matures to the point where it can meaningfully accelerate gravitational n-body simulations, even in specialized or partial ways, cosmologists studying dark matter structure formation would likely be among the most eager potential users of that technology, given how computationally expensive their existing classical simulations already are. This is a reasonable, well-grounded hope rather than an established achievement, and it is important to be clear that no published research currently claims quantum computers have meaningfully accelerated dark matter structure simulations or provided new insight into the early expansion of the universe. What does exist is a smaller, more modest body of theoretical work exploring how quantum algorithms designed for chaotic and multi-body systems, including the algorithms being tested on simplified three-body configurations, might, in principle, be extended toward these much larger cosmological simulations someday, a natural next step in the research roadmap rather than a current capability. Scientific honesty requires holding both of these things at once. Genuine optimism about a promising research direction, paired with clarity about how much work remains before that promise becomes a demonstrated reality. Stepping back from dark matter and cosmology, it is worth returning to the more immediate and tangible territory of star clusters, because this is where the three-body problem naturally scales upward into something even richer. Globular clusters, those densely packed spherical swarms containing anywhere from tens of thousands to millions of stars, bound together by their mutual gravity, represent nature's own laboratory for extreme multi-body dynamics. Within the crowded core of a globular cluster, stars pass close enough to each other with enough frequency that three-body and even higher order gravitational encounters happen regularly over the cluster's lifetime, ejecting stars, forming tight binary pairs, and occasionally triggering the kind of close encounters that astronomers believe can produce exotic objects like blue stars that appear anomalously young and massive compared to their neighbors because they formed through stellar mergers or mass transfer triggered by chaotic multi-body interactions, simulating the full dynamical history of a globular cluster, tracking every gravitational interaction among hundreds of thousands or millions of stars across billions of years, is a computational challenge that dwarfs even the ordinary three-body problem in raw complexity, though interestingly it often becomes more computationally tractable in aggregate through statistical and averaging techniques that treat the cluster's overall behavior more like a fluid or a gas than as an enormous collection of individually tracked, chaotic, three-body problems. This connects back to something quietly profound about chaos in gravitational systems, which is that chaos at the level of individual trajectories does not necessarily prevent scientists from making confident, well-tested statistical predictions about the system as a whole, even though nobody can predict exactly where a single star within a globular cluster will be positioned. After several billion years of chaotic gravitational shuffling, astronomers can predict with considerable confidence the overall rate at which stars escape the cluster, the general shape the cluster's stellar density profile will take, and the statistical likelihood of various kinds of close encounters occurring over the cluster's lifetime, because these aggregate statistical properties turn out to be far more stable and predictable than any individual trajectory. This distinction between unpredictable individual trajectories and predictable statistical outcomes is one of the genuinely elegant discoveries chaos theory has offered physics, and it applies just as much to the three-body problem itself, where, even though the exact fate of any single simulated triple-star system remains chaotic and unpredictable in detail, researchers running large statistical ensembles of many thousands of slightly varied initial configurations can still confidently report the overall probability that a given type of triple system ends in an ejection, a stable hierarchical arrangement, or a collision, which is exactly the kind of statistical mapping both classical and quantum researchers are working to refine and accelerate. It is worth spending a little more time on how researchers are actually attempting to bridge classical and quantum computing in this field today, because the reality is less about a pure quantum computer replacing a classical one, and much more about hybrid approaches that let each type of hardware contribute what it does best. Most of the quantum algorithms currently being tested for optimization and simulation problems, including variational quantum eigensolvers and the quantum approximate optimization algorithm, are explicitly hybrid in design. A classical computer handles the bulk of the bookkeeping, adjusting parameters and interpreting results, while a quantum processor is called upon repeatedly to evaluate a specific mathematical quantity that is believed to be hard for classical computers to estimate efficiently. This back and forth between classical and quantum hardware happens many times over the course of solving a single problem, with the classical computer using something called an optimization loop to gradually refine the parameters fed into the quantum processor, nudging the combined system toward better and better answers with each iteration. This hybrid architecture reflects an honest engineering reality. Today's quantum processors are simply too small and too error-prone to run an entire complex calculation, like simulating a chaotic three-body system across a long time span, entirely on quantum hardware without assistance from classical computing at nearly every step. Error correction represents perhaps the single largest technical hurdle standing between today's noisy, error-prone quantum processors and the kind of large-scale, high-fidelity quantum simulations that would be needed to meaningfully outperform classical supercomputers on problems like gravitational chaos. Quantum error correction works by spreading a single unit of reliable quantum information, sometimes called a logical qubit, across many physical qubits, using redundancy and clever encoding schemes to detect and correct errors without directly measuring, and thereby destroying the fragile quantum state itself. The overhead required is substantial. Some early theoretical estimates suggested that a single reliable logical qubit might require dozens, or even hundreds, of physical qubits working together to achieve the low error rates needed for genuinely useful, large-scale quantum algorithms. Research groups around the world have made steady, incremental, and genuinely impressive progress on error correction throughout the 2020s, demonstrating logical qubits that outperform the physical qubits used to construct them for the first time in carefully controlled experiments, published in leading physics journals. A milestone many researchers consider one of the most important developments in the entire field, since it represents the first concrete evidence that the error correction overhead can actually pay for itself as hardware scales up. While we are on the subject of what remains genuinely unresolved, it is worth revisiting the three-body problem's own mathematical history a little further, because the story did not end with Poincare's discovery of sensitive dependence on initial conditions. For a long time after Poincare's work, many mathematicians assumed the three-body problem simply had no useful general solution at all, chaotic and therefore mathematically hopeless beyond numerical approximation. That assumption was not entirely correct. In 1912, the Finnish mathematician Carl Sundman published a genuine mathematical breakthrough, proving that a formal, convergent series solution to the three-body problem does exist for almost all initial conditions, expressed as an infinite sum that, in principle, converges to the exact positions of the three bodies at any point in time. This might sound like it should have settled the whole matter, But Sundman's solution turned out to be a curious mathematical footnote rather than a practical tool, because the series converges so agonizingly slowly that an impractically enormous number of terms, some estimates placing the figure at well beyond 10 to the millionth power, would be required to calculate the positions with even modest useful precision. In other words, a rigorous, mathematically exact solution exists, but it is so computationally impractical that it offers essentially no help to anyone trying to actually predict where three real stars will be at a specific future moment. A wonderfully humbling reminder that mathematical existence and practical usefulness are not always the same thing. This peculiar history matters for our story because it reframes what quantum computing, machine learning, and improved classical algorithms are actually trying to achieve. Nobody working in this field today is trying to find some elegant closed-form equation that magically predicts three-body motion the way Newton's equations predict two-body motion. The chaos is real. It is mathematically proven, and no computing paradigm, quantum or otherwise, is expected to eliminate it. What every serious research effort is actually chasing instead is something more modest and, in its own way, more interesting. Faster and more efficient ways to compute reliable predictions within the finite window of time before chaos inevitably takes over. Better statistical characterizations of the full range of possible outcomes once that window closes, and deeper insight into which regions of the vast space of possible three-body configurations tend to produce long-lived stability rather than rapid disintegration. Quantum computing, in the most honest and currently accurate assessment available, is one of several promising tools being explored to chip away at these more modest but still scientifically valuable goals. Not a technology that has already rendered chaos obsolete. There is another entire dimension to this story that pushes beyond ordinary Newtonian gravity altogether. And that is what happens to the three-body problem once you take Einstein's general relativity seriously, particularly in extreme environments involving black holes. When three black holes, or a black hole embedded within a binary system alongside another massive companion, interact gravitationally at close range, the dynamics become even richer and stranger than the classical three-body problem, because general relativity introduces effects entirely absent from Newtonian gravity, including the gradual loss of orbital energy through the emission of gravitational waves. Ripples in space-time itself, predicted by Einstein in 1916 and directly detected for the first time by the Laser Interferometer Gravitational Wave Observatory in 2015, a discovery announced to the public the following year and later recognized with a Nobel Prize in Physics. Hierarchical triple systems involving black holes, where an inner binary black hole pair orbits within a wider system alongside a third massive object, have become an area of intense research interest because the gravitational influence of that third, more distant body can, through a subtle effect known as the Kozai-Lidov mechanism, periodically drive the inner binary's orbit to become far more eccentric than it would be on its own, sometimes eccentric enough to trigger a merger between the two inner black holes that would otherwise have taken far longer, or never happened at all, without the third body's gravitational nudging. This relativistic three-body physics connects to gravitational wave astronomy in a genuinely exciting way, because the distinctive gravitational wave signal produced by a black hole merger driven by this kind of triple-body dynamical interaction can, in principle, look subtly different from a merger between an isolated binary pair that never had a third gravitational companion influencing its history. Detecting and correctly interpreting these subtle signatures requires enormously sophisticated data analysis, sifting through the extraordinarily faint ripples captured by gravitational wave detectors, and comparing them against vast libraries of theoretically predicted waveforms generated by Classical numerical relativity simulations, themselves among the most computationally demanding calculations in all of physics, since they require solving Einstein's notoriously complex field equations for objects in extreme, rapidly changing gravitational environments. Some researchers have begun exploring whether quantum computing might eventually assist with these numerical relativity calculations, given how computationally intensive they already are using purely classical methods. Though, as with the classical three-body problem itself, this remains an early stage, research direction rather than an operational technique currently used by a working gravitational wave. Astronomers, quantum technology does have one area of gravitational science where its contribution today is considerably more mature and already delivering practical, verified results, and that is quantum sensing. A somewhat different application than quantum computing, but built on closely related physical principles. Instruments called atom interferometers exploit the wave-like superposition-based nature of individual atoms, cooled to temperatures near absolute zero and split into a quantum superposition of two different paths, to measure gravitational fields and accelerations with extraordinary precision. Precision that in some laboratory demonstrations has exceeded the sensitivity of the best classical accelerometers and gravimeters available. Researchers have proposed, and in some cases begun prototyping, gravitational wave detectors based on these quantum sensing techniques, potentially complementing the laser interferometer technology used by existing observatories and extending sensitivity into frequency ranges that current detectors cannot easily access. This is a genuinely mature, actively developing application of quantum physics to gravitational science. Worth mentioning precisely because it illustrates that quantum technology's real contributions to understanding gravity so far have come more from ultra-precise measurement than from ultra-powerful computation. A nuance easily lost in headlines that lump every quantum-related advance together under one sweeping narrative of quantum computers conquering gravity itself, turning back toward computation. It is worth acknowledging plainly which major research institutions and companies are actually driving the small but real steps forward in applying quantum algorithms to chaotic and gravitational simulation problems, since naming real, verifiable efforts helps separate honest reporting from vague, unattributed claims of breakthroughs. University, physics, and computer science departments around the world, often working in partnership with national laboratories that operate some of the most advanced quantum hardware available for research purposes, have published peer-reviewed papers over the past several years exploring quantum algorithms for simplified chaotic oscillator systems, small-scale gravitational encounter simulations, and optimization-based approaches to stability analysis in restricted versions of the three-body problem, meaning versions where one of the three masses is assumed to be negligibly small compared to the other two, a simplification that makes the mathematics considerably more tractable, while still preserving much of the genuinely chaotic behavior that makes the full problem so interesting. These are careful, incremental, properly peer-reviewed contributions to a genuinely promising field. Exactly the kind of steady scientific progress that rarely generates dramatic headlines, but that quietly builds the actual foundation upon which any future practical quantum advantage in this area would eventually be built. The mention of islands of stability within chaotic systems deserves a much closer, more rigorous look than a passing phrase, because it turns out to rest on one of the most beautiful and genuinely surprising results in all of mathematical physics, discovered decades before anyone imagined applying quantum computers to the problem. Mathematicians studying dynamical systems in the middle of the 20th century, particularly Andrei Kolmogorov, Vladimir Arnold, and Jürgen Moser, whose combined contributions are now honored together as the Kolmogorov-Arnold-Moser theorem, proved something that initially seems almost paradoxical given everything we have discussed about chaos. Even within systems that are chaotic overall, there can exist surviving pockets of quasi-periodic, bounded, essentially stable motion, provided the perturbation pushing the system away from an idealized, perfectly solvable configuration is sufficiently small and the system's underlying frequencies are, in a precise mathematical sense, sufficiently irrational, meaning they do not fall into simple, resonant numerical ratios with each other. These surviving stable regions form intricate, fractal-like structures nested within the broader chaotic sea when mapped mathematically, and they explain, among other things, why our own solar system, despite technically qualifying as a many-body gravitational system with all the theoretical potential for chaos that implies, has nonetheless remained relatively stable over billions of years, its planets tracing orbits that wobble and shift subtly over immense timescales without spiraling into the kind of dramatic, system-destroying chaos that can afflict less fortunately arranged multi-star systems. This is precisely the mathematical territory that both classical numerical searches and the emerging quantum optimization approaches we discussed earlier are trying to map more efficiently, hunting for these Kolmogorov-Arnold-Moser islands of stability hidden within the vast parameter space of possible three-body configurations. Classical researchers have spent decades developing sophisticated numerical techniques to locate and characterize these stable islands for specific mass ratios and orbital configurations, building extensive published catalogues of known, stable, three-body solutions, including a particularly celebrated and almost whimsical discovery in the year 2000 of a stable, periodic three-body orbit shaped like a figure eight, in which three equal masses chase each other endlessly around a single looping path without ever colliding or drifting apart. A solution so elegant and unexpected when it was first published that it generated genuine excitement across the mathematical physics community and inspired a wave of further research, uncovering dozens of additional stable, periodic three-body solutions in the years that followed, each occupying its own small, precisely defined island within the surrounding chaotic sea. Finding new members of this growing family of stable periodic solutions is exactly the kind of structured search problem that researchers hope quantum optimization algorithms might eventually accelerate, since it involves searching a vast, continuous space of possible mass ratios, orbital shapes, and starting configurations for the comparatively rare combinations that produce bounded, non-chaotic, indefinitely repeating motion rather than eventual disintegration. A handful of published theoretical papers have begun exploring exactly this application, formulating the search for stable periodic three-body orbits as an optimization problem suitable for quantum annealing or variational quantum algorithms, with early, small-scale results, suggesting the approach is mathematically sound even if the hardware available today remains far too limited to meaningfully outperform the classical numerical searches that discovered the figure 8 orbit and its many known relatives. This is a wonderful, concrete example of exactly the kind of measured, honest optimism that characterizes the most credible corners of this research field. A real mathematical structure worth searching for, a real computational challenge in searching for it efficiently, and a real, still unproven hope that quantum computing might eventually help. All held together without inflating any single piece into more than it currently is. Stepping even further back, it is worth reflecting on why chaos and unpredictability in systems like the three-body problem carry a weight that extends beyond astrophysics into deeper questions about the nature of prediction and determinism itself, a connection that has fascinated philosophers of science almost as much as physicists. In the early 19th century, the mathematician and astronomer Pierre-Simon Laplace articulated a famous thought experiment, now often called Laplace's demon, imagining a hypothetical intelligence that, if it knew the precise position and momentum of every particle in the universe at a single instant, could, in principle, use the deterministic laws of physics to calculate the entire future and the entire past with perfect certainty, leaving no room for genuine unpredictability anywhere in nature. The three-body problem, and chaos theory more broadly, complicates this picture in a genuinely profound way, not by breaking determinism itself, since the underlying equations of motion remain perfectly deterministic, but by demonstrating that even a deterministic universe can produce outcomes that are, for all practical purposes, permanently unpredictable to any finite observer, because the computational and measurement precision required to forecast a chaotic system's distant future would need to be, quite literally, infinite. This distinction between true randomness and merely practical unpredictability turns out to matter quite a bit when quantum computing enters the conversation, because quantum mechanics introduces a genuinely different, and in some interpretations, more fundamental, kind of unpredictability into physics than classical chaos does. When a quantum system is measured, the specific outcome obtained, according to the standard interpretation of quantum mechanics developed largely through the work of physicists such as Niels Bohr and Werner Heisenberg in the 1920s, is not merely unpredictable due to our incomplete knowledge, the way a chaotic classical system is, but is considered by most working physicists to be fundamentally irreducibly random, with no hidden underlying variables determining the outcome in advance. A conclusion strongly supported by decades of experimental tests of Bell's theorem, confirming that no local hidden variable theory can reproduce the statistical predictions of quantum mechanics. This means that a quantum computer attempting to simulate a classical chaotic system like the three-body problem is, in a philosophically interesting twist, using a physically random substrate to model a system that is technically deterministic but practically unpredictable. A curious pairing that some researchers have suggested might actually offer subtle advantages for certain kinds of statistical sampling tasks relevant to chaos research, since quantum hardware can, in principle, generate certain kinds of random or probabilistic samples more efficiently and with better statistical properties than classical pseudo-random number generators, which are themselves only deterministic approximations of true randomness. It would be a mistake, however, to let this elegant philosophical connection between quantum randomness and classical chaos overstate the practical case for quantum computing's near-term usefulness in this field. An honest science communication requires acknowledging a genuinely important counterpoint that has emerged from within the quantum computing research community itself over the past several years, sometimes referred to as several times since quantum computing research accelerated in earnest. Clever classical computer scientists have discovered that algorithms initially believed to require a quantum computer for their theoretical speed advantage could, with sufficiently creative classical reformulation, be replicated on ordinary classical hardware with only a modest, rather than exponential, loss of efficiency, effectively closing the gap that originally made a particular quantum algorithm exciting. This pattern has played out enough times in the research literature that experienced quantum computing researchers now treat claims of dramatic quantum advantage with careful, appropriate skepticism until independent classical researchers have had a genuine opportunity to search for a dequantized alternative, a healthy scientific norm that any honest account of quantum computing's applications to chaotic, gravitational systems should keep firmly in view. Given all of this careful nuance, it is fair to ask what a realistic, evidence-based roadmap for quantum computing's contribution to gravitational chaos research might actually look like over the coming years, rather than the coming decades of speculative science fiction. Most researchers working in the field describe a staged progression rather than a single dramatic breakthrough moment. The near-term stage, largely already underway, involves continued small-scale proof of concept demonstrations on increasingly capable but still noisy hardware, refining the mathematical formulations that translate chaotic dynamical systems into forms suitable for quantum processing, and building the hybrid classical quantum software infrastructure needed to actually run these algorithms in practice. A middle stage, which many researchers cautiously project sometime within the coming decade based on current error correction progress, would involve quantum processors reaching what specialists call the early fault-tolerant regime, where a modest number of genuinely reliable, error-corrected logical qubits become available, likely enough to tackle somewhat larger, simplified chaotic systems than today's noisy hardware can manage, though still probably well short of full-scale astrophysical simulations. A later, considerably more speculative stage, requiring substantially larger numbers of fault-tolerant logical qubits than anyone has yet demonstrated, would be needed before quantum hardware could plausibly outperform classical supercomputers on genuinely large scale. High-resolution gravitational chaos simulations of the kind that would meaningfully assist real astronomical research or spacecraft mission planning. It is worth being explicit that this staged roadmap comes with substantial uncertainty at every step, a fact that responsible researchers in the field readily acknowledge rather than paper over. Quantum computing has, at various points over the past 2 decades, both exceeded and fallen short of expert predictions, sometimes achieving milestones ahead of schedule through unexpected engineering breakthroughs, and at other times encountering stubborn technical obstacles that pushed projected timelines back by years. Given this history, the most scientifically responsible stance to take toward claims about quantum computing's future role in solving problems, like the three-body problem, is one of genuine, engaged curiosity paired with patient skepticism, tracking the steady accumulation of peer-reviewed, independently verified results, rather than getting swept up in any single dramatic announcement, however exciting the headline framing might sound. Before we move toward drawing all of these threads together, it is worth highlighting one corner of three-body physics that is not speculative at all, but rather one of the most practically important and thoroughly solved special cases within the entire field, because it offers a useful contrast to everything chaotic we have discussed so far. Long before Poincare discovered the chaotic general case, the mathematicians Leonhard Euler and Joseph Louis Lagrange, working independently in the 1770s, discovered that a highly simplified version of the three-body problem, now called the restricted three-body problem, in which the mass of the third body is so small that it exerts negligible gravitational influence on the two larger bodies, while still being influenced by them, actually does admit exact, stable, elegant solutions under specific conditions. Lagrange in particular identified 5 special points in the vicinity of any 2 massive orbiting bodies, now called Lagrange points in his honor, where the combined gravitational pull of the 2 large bodies and the centrifugal effect of orbital motion balance out in such a way that a much smaller third object placed there can maintain a stable, or in some cases metastable, position relative to the 2 larger bodies indefinitely, without being pulled away by the chaotic dynamics that plague the general three-body problem. This is far from a purely academic curiosity. Space agencies rely on Lagrange points constantly for real, operational missions, and the most prominent recent example is genuinely worth pausing on. The James Webb Space Telescope, launched in December of 2021 and now one of humanity's most scientifically productive observatories, orbits not the Earth directly, but a location roughly 1.5 million kilometers from Earth known as the second Lagrange point, or L2, a gravitationally balanced position along the line connecting the Sun and Earth. Positioned on the side opposite the Sun, at this Lagrange point, the combined gravitational pull of the Sun and Earth, along with the orbital dynamics involved, allows the telescope to orbit the Sun in careful synchronization with the Earth, while requiring only occasional small trajectory correction maneuvers to maintain its position, all calculated using classical orbital mechanics, rooted directly in Lagrange's 18th century mathematical solution to the restricted three-body problem. This stands as a beautiful, concrete reminder that even within a field defined largely by chaos and unpredictability, careful mathematical analysis can still uncover genuinely stable, exploitable structures. Precisely the same kind of island of order within chaos that both classical researchers and today's emerging quantum algorithms are hunting for throughout the broader, unrestricted version of the problem. Chaos theory's reach extends well beyond gravitational physics too, and drawing that connection helps explain why so many researchers across wildly different fields have taken an interest in whatever computational tools, quantum or otherwise, might help characterize chaotic systems more efficiently. The meteorologist Edward Lorenz, working at the Massachusetts Institute of Technology in the 1960s, stumbled onto sensitive dependence on initial conditions from an entirely different direction than Poincare had, while running a simplified computerized weather model and discovering, almost by accident, that rounding a single input value slightly differently produced wildly divergent forecasts after only a modest, simulated time period. Lorenz's observation, later popularized under the evocative phrase the butterfly effect, suggesting that the flap of a butterfly's wings in one part of the world could, in principle, influence the formation of a storm system elsewhere weeks later, helped establish chaos theory as a serious, unified field of study spanning weather prediction, fluid dynamics, population biology, economics, and, of course, gravitational mechanics. All fields that share the same fundamental mathematical signature of deterministic equations producing practically unpredictable long-term outcomes. This shared mathematical foundation is precisely why progress made on quantum algorithms for one chaotic system, whether a simplified three-body gravitational configuration or an idealized fluid dynamics model, often carries genuine, transferable insight for researchers working on entirely different chaotic systems elsewhere in science, since the underlying computational challenges, representing exponentially diverging trajectories, efficiently, and searching vast parameter spaces for pockets of stability, recur again and again across disciplines that otherwise have little in common. Weather forecasting, in particular, offers a useful down-to-earth comparison for calibrating expectations about what quantum computing might eventually offer gravitational chaos research, precisely because meteorologists have spent decades wrestling with an analogous chaotic prediction problem using purely classical tools, developing sophisticated techniques such as ensemble forecasting, running many slightly varied simulations in parallel and interpreting the spread of outcomes statistically, rather than chasing a single, impossibly precise deterministic forecast far beyond the point where chaos renders such precision meaningless. This ensemble approach, born directly out of Lorenz's own chaos theory insights, has proven remarkably effective at extending the practically useful range of weather forecasts considerably further than a single deterministic simulation ever could, even without any quantum computing involved whatsoever. and it offers a valuable lesson for gravitational chaos research as well. Namely, that clever statistical and algorithmic reformulation of a problem can sometimes deliver more practical improvement than waiting for a single dramatic hardware breakthrough, whether that breakthrough eventually comes from quantum computing, more powerful classical supercomputers, or some combination of both working together. Real triple star systems, once you start looking for them, turn out to be considerably more common in the night sky than casual observation suggests. And a few well-studied examples help ground everything we have discussed in tangible, observable astronomy rather than abstract mathematics. The star system, Algol, visible to the naked eye in the constellation Perseus and known since antiquity for its distinctive periodic dimming that ancient observers found unsettling enough to nickname it the demon star, is actually a hierarchical triple system, consisting of a close eclipsing binary pair, whose mutual eclipses cause the famous dimming, orbited by a third, more distant, stellar companion. A configuration astronomers only fully confirmed through detailed spectroscopic and interferometric observations accumulated over the 20th century. Polaris, the star most people know simply as the North Star, prized throughout human history for its usefulness in navigation, because it sits almost perfectly aligned with Earth's rotational axis, is likewise not a solitary star at all, but the anchor of its own multiple star system, with at least two smaller stellar companions confirmed through precise astrometric measurements. A small hierarchical family rather than the single point of light it appears to be from Earth. These confirmed examples also invite an honest acknowledgement of how astronomy sometimes gets multi-star system claims wrong, before eventually getting them right. A healthy reminder that scientific caution matters just as much when interpreting observational data as it does when interpreting computational claims about quantum breakthroughs. In the early 2000s, a research team announced the detection of a planet orbiting within a close triple star system catalogued under a designation drawn from the Henry Draper Star Catalog, a claim that generated considerable excitement at the time given how dynamically challenging planetary formation and long-term orbital stability would be within such a tightly packed, gravitationally chaotic multi-star environment. Subsequent observations by independent research teams, however, failed to confirm the original detection, and the consensus within the astronomical community eventually shifted toward treating the original claim as most likely a false positive, rather than a genuine planetary discovery. A quiet but important correction that rarely made headlines with anything like the fanfare of the initial announcement. Stories like this one are worth remembering precisely because they illustrate, in a completely different corner of astronomy, the same broader lesson this whole exploration of quantum computing and the three-body problem keeps circling back to: that genuine scientific progress in chaotic, difficult to observe systems tends to arrive slowly, provisionally, and subject to correction, rather than through single, dramatic, unqualified announcements with that grounding in real, observed astronomy firmly in place. It becomes possible to appreciate what a genuinely mature, properly validated quantum contribution to three-body research might eventually look like, rather than the exaggerated version sometimes described in less careful accounts. Imagine a future observatory detecting a newly discovered close triple star system through direct imaging or precise astrometric measurement, the kind of detection space telescopes and ground-based observatories make with increasing frequency as instrumentation continues improving. Astronomers studying that system would want to know several things quickly: whether the configuration is likely to remain stable over astronomically relevant timescales, what range of possible future configurations the system might evolve through, given the measurement uncertainties in its current observed positions and velocities, and whether the system sits near one of those precious Kolmogorov-Arnold-Moser islands of long-term stability, or within a more precarious, chaotic region of parameter space likely to eject a member relatively soon. A sufficiently mature quantum optimization algorithm, running on sufficiently advanced error-corrected hardware, could, in principle, help astronomers explore that vast space of possible future configurations more efficiently than classical numerical integration alone, particularly if many such systems needed similar analysis across a large observational survey, effectively acting as an accelerant for a well-defined statistical search problem rather than as some kind of magic crystal ball producing a single, certain prediction. This more modest, carefully bounded vision of quantum computing's eventual contribution is, frankly, a more exciting and more scientifically credible story than the sensationalized alternative, precisely because it fits coherently within everything else we understand about chaos, computation, and the genuine, hard-won limits of predictability that Poincare identified more than a century ago, and that no computing paradigm, however powerful, is expected to fully erase. The three-body problem was never going to be solved in the sense of producing a single, definite forecast for any specific chaotic system extending indefinitely into the future, because Poincare and later mathematicians proved, rigorously and permanently, that such a forecast is not merely difficult but fundamentally impossible. Beyond a certain time horizon for genuinely chaotic configurations, what remains genuinely open, genuinely exciting, and genuinely worth continued research, investment, is the considerably more tractable and more useful question of how efficiently we can characterize the statistical landscape of possible outcomes within that inherent uncertainty, and on that narrower, more honest question, quantum computing represents one promising, still developing tool among several, working alongside classical numerical methods and machine learning rather than replacing them. It is also worth acknowledging the practical, human side of this research effort, because quantum computing applied to chaotic physical systems is not happening in some isolated theoretical vacuum, but within a rapidly growing, increasingly well-funded international research ecosystem. Government, science agencies in multiple countries have designated quantum information science as a strategic research priority over the past several years, funding dedicated national quantum initiatives that support university research groups, national laboratories, and public-private partnerships aimed at advancing both quantum hardware and quantum algorithm development. Private companies building quantum processors have simultaneously grown their own internal research, divisions exploring scientific applications beyond the more immediately commercial areas like cryptography and optimization, often collaborating directly with academic physicists, specifically because problems like chaotic, gravitational dynamics offer rich, well-defined mathematical structure that makes for excellent algorithm development test cases, even when practical, large-scale advantage remains years away. This combination of academic curiosity, national strategic investment, and private sector research capacity has produced a genuinely vibrant, rapidly publishing research community, one that presents new results at physics and computer science conferences with real regularity, even though, as we have discussed at length, the pace of genuinely validated breakthroughs remains considerably more measured and incremental than popular coverage sometimes suggests. Graduate students and early career researchers entering this field today find themselves working at a genuinely unusual moment in the history of both physics and computer science, one where the tools available to them are advancing quickly enough that techniques considered cutting-edge only a few years earlier can become almost standard practice by the time a doctoral research project concludes. while simultaneously working within a field mature enough, thanks to Poincare, Sundman, Kolmogorov, Arnold, Moser, Lorentz, and generations of subsequent researchers, to offer a genuinely deep, well-established theoretical foundation to build new quantum approaches upon, rather than starting entirely from scratch. This blend of a fast-moving technological frontier layered on top of a century and a half of rigorous, hard-won mathematical understanding is precisely what makes this particular corner of physics such a compelling case study for anyone curious about where computation and fundamental science are headed together in the years immediately ahead. So where does all of this actually leave us, once the exaggerated headlines are set aside and replaced with the more careful, evidence-grounded picture we have built up piece by piece throughout this exploration? The three-body problem remains, and will always remain, chaotic in the rigorous mathematical sense first uncovered by Poincare, meaning long-term. Precise prediction of any specific chaotic configuration is not a temporary limitation, waiting for better technology to overcome, but a permanent, mathematically proven feature of how these systems behave. Quantum computing has not solved the three-body problem, has not yet reliably forecast the long-term fate of any specific real star system beyond what classical methods already achieve, and is not currently being used to plot operational spacecraft trajectories through multi-star environments. All claims that circulate in less careful corners of science communication, but that outrun what the peer-reviewed research literature actually supports as of the most recent published work available. What quantum computing genuinely offers today, in this specific corner of physics, is a promising, actively developing set of theoretical and small-scale experimental approaches to the more modest but still valuable questions surrounding chaotic gravitational systems, faster statistical characterization of possible outcomes, more efficient searches for the rare, mathematically beautiful islands of stability like the Figure 8 orbit nestled within the broader chaotic landscape, and a genuinely interesting theoretical bridge between the deterministic unpredictability of classical chaos and the fundamentally probabilistic nature of quantum mechanics itself, the honest frontier that remains. And it is a genuinely exciting one worth watching closely in the years ahead. Involves several concrete open questions researchers are actively working to answer. Whether quantum hardware can scale past today's noisy, error-prone limitations quickly enough, and with a favorable enough error correction overhead, to eventually tackle chaotic simulations at a scale and fidelity that meaningfully exceeds what classical supercomputers, aided by increasingly sophisticated machine learning techniques, can already achieve on their own. Whether the theoretical connections between quantum uncertainty and classical chaos can be translated into genuinely practical algorithmic advantages, rather than remaining an elegant but computationally inert mathematical curiosity. Whether hybrid classical quantum approaches, already proving useful for smaller optimization problems in logistics and chemistry, can be successfully adapted to the specific mathematical structure of gravitational many-body dynamics at scales relevant to real astrophysical research, and whether, as quantum hardware inevitably continues its steady, carefully documented march toward larger qubit counts and lower error rates, the field will eventually cross a genuine, independently verified threshold where quantum simulation of chaotic gravitational systems moves from promising research direction to practical scientific tool. The same kind of threshold that classical computing itself crossed decades earlier when room-sized mainframes first made numerical orbital integration a routine part of astronomical practice. There is a particularly fitting way to bring this exploration full circle by looking toward the future of interstellar exploration itself. since any eventual human or robotic mission to a triple star system, including Alpha Centauri, would need exactly the kind of sophisticated multi-body trajectory planning we have spent this entire journey carefully examining. Serious scientific proposals for sending probes toward the Alpha Centauri system have existed for years. Most notably, concepts exploring whether tiny, laser-propelled spacecraft could be accelerated to a meaningful fraction of the speed of light, potentially reaching the system within a human lifetime rather than the tens of thousands of years a conventional chemical rocket would require. Any such mission, should it ever move beyond the conceptual and early engineering stage it currently occupies, would eventually need extraordinarily precise trajectory calculations for navigating within the destination system itself, especially given that, as we discussed earlier, Alpha Centauri is not a single star but a hierarchical multiple system, meaning a probe approaching the system would need trajectory planning sophisticated enough to account for the combined, evolving gravitational influence of at least two, and depending on final approach geometry, potentially all three, stellar components. Whether that future trajectory planning ultimately relies on refined classical numerical methods, the kind that have reliably guided every successful deep space mission flown to date, on machine learning techniques trained to rapidly evaluate candidate trajectories, the way researchers have already demonstrated for simplified three-body classification problems, on quantum optimization algorithms running on hardware considerably more mature than anything available today, or, as seems most likely given how these fields tend to develop in practice, on some thoughtfully engineered combination of all three working in concert, remains genuinely unknown and will likely depend heavily on how quickly each of these technologies continues to mature over the coming decades. What can be said with confidence today is that the underlying physics such a mission would need to navigate, the same chaotic, sensitively dependent, mathematically rich dynamics Poincare first glimpsed while chasing a prize problem about the stability of our own solar system more than a century ago, will remain exactly as challenging, exactly as beautiful, and exactly as scientifically important, regardless of which computational tool eventually proves best suited to taming it. Taking a step back across everything this exploration has covered, from Newton's original to body triumph through Poincare's humbling discovery of chaos, from Sundman's mathematically valid but practically useless infinite series through the elegant discovery of the figure 8 orbit and the broader family of Kolmogorov-Arnold-Moser stability islands, from the earliest room-sized classical computers through today's carefully cooled, still noisy quantum processors, a consistent and genuinely reassuring pattern emerges. Every generation of researchers who has taken the three-body problem seriously has found the honest, unglamorous work of careful mathematics and patient computation more valuable, in the long run, than any premature declaration of victory over chaos. That pattern holds just as true for quantum computing's emerging role in this story, as it did for every classical computational advance that came before it. The technology is genuinely promising. The theoretical foundations connecting quantum information science to chaotic dynamics are genuinely elegant, and the small-scale experimental results published so far are genuinely encouraging for a still young field. None of that requires exaggeration to be exciting. The real story, patiently unfolding across university laboratories, national research facilities, and peer-reviewed journals around the world, is more interesting precisely because it respects the genuine difficulty of the problem. Poincare identified, rather than pretending the difficulty has already been erased, what researchers still do not know, and are actively working to find out, includes exactly how large and how error-corrected quantum hardware will need to become before it offers a demonstrable, independently verified advantage over the best classical and machine learning approaches for chaotic gravitational simulation specifically, whether the theoretical bridge between quantum uncertainty and classical chaos can be engineered into a practical algorithmic tool rather than remaining an elegant mathematical observation. How many additional stable periodic orbits remain to be discovered within the vast, largely unmapped parameter space of possible three-body configurations, and how the statistical patterns astronomers have already observed in real hierarchical star systems will hold up as observational surveys continue growing more sensitive and more comprehensive in the years ahead. Current research continues on every one of these fronts simultaneously, spanning small-scale quantum hardware experiments, ever more refined classical numerical integrators, expanding machine learning training sets built from ever larger libraries of simulated trajectories, and steadily improving astronomical surveys capable of detecting and characterizing real, multi-star systems with greater precision than ever before. Future discoveries in this space will likely arrive the same way most of the genuine progress chronicled throughout this exploration has arrived, incrementally, carefully, and through the accumulated, cross-checked work of many independent research groups, rather than through any single dramatic announcement. The three-body problem endures as one of physics' most important open questions, not because it resists every form of progress, but because it sits at a rare and genuinely fascinating intersection, a system simple enough to state in a single sentence: three masses obeying Newton's law of gravity, yet complex enough in its behavior to have humbled the finest mathematical minds for more than 3 centuries and to still be actively reshaping how physicists think about prediction, chaos, and the fundamental limits of computation itself. Whatever role quantum computing ultimately plays in the next chapter of that long story, the deeper lesson embedded in Poincare's original discovery remains as relevant today as it was in the 1890s. That even a universe governed entirely by precise, deterministic physical laws can still hold genuine, permanent surprises for anyone patient enough to keep looking closely, and curious enough to keep asking what those three chaotically dancing stars will do next. One phrase worth addressing directly, since versions of it circulate widely in popular discussions of this topic, is the idea of building a complete digital twin of a star system inside a quantum computer, a term borrowed from engineering, where it describes a detailed virtual model of a physical system, such as a jet engine or a manufacturing plant, kept continuously synchronized with real-world sensor data so engineers can test scenarios virtually before applying changes to the actual physical system. Digital twin technology is a real, well-established, and genuinely useful engineering practice, extensively used across aerospace, manufacturing, and infrastructure management. But applying that same term to an entire chaotic star system carries some important caveats worth spelling out plainly. A true digital twin depends on continuous high-fidelity sensor data feeding back from the real system to keep the virtual model synchronized and accurate, something readily available for a jet engine wired with hundreds of physical sensors, but considerably harder to achieve for a star system light years away, where astronomers must reconstruct positions and masses indirectly through painstaking spectroscopic and astrometric observation, rather than direct sensor measurement. Even a perfectly synchronized digital twin of a chaotic three-body system, whether built on classical or quantum hardware, would still run headlong into the same Lyapunov time limitations discussed earlier, since the chaos itself, not the fidelity of the initial model, is what eventually destroys long-term predictive accuracy. Using the digital twin metaphor for a chaotic star system is not inherently misleading. It can be a genuinely useful way to describe the goal of building an increasingly accurate, continuously refined virtual model, but it should not be mistaken for a claim that such a model, once built, could somehow escape the fundamental unpredictability that Poincare proved is baked into the mathematics of chaotic gravitational systems themselves. This same instinct toward careful, precise language applies just as strongly to how quantum annealing gets described in popular accounts of this research area, since the actual mechanism at work is considerably more specific and in its own way more elegant than vague descriptions of a system exploring every possibility at once might suggest. A quantum annealer is built to solve a particular mathematical formulation called a quadratic, unconstrained binary optimization problem, essentially a carefully structured way of encoding a search for the lowest energy, or optimal arrangement among a large number of interrelated binary choices. Engineers configure the hardware so that its physical qubits are coupled together in a pattern that mirrors the mathematical structure of whatever problem is being solved, then allow the entire system of qubits to gradually settle from an easily prepared, simple starting state into a final, low-energy configuration through a slow, carefully controlled process called quantum annealing. Drawing an intentional analogy to the metallurgical process of annealing, in which a heated metal is cooled slowly to allow its atomic structure to settle into a low-energy, more stable crystalline arrangement rather than a disordered one. Translating the search for stable three-body configurations into this quadratic, unconstrained binary optimization format requires careful, non-trivial mathematical work. Encoding continuous physical quantities, like orbital positions and velocities, into the discrete binary variables the annealer actually operates on, and refining that encoding remains an active area of algorithm design research in its own right, quite apart from whatever progress happens on the physical hardware itself. Understanding these specific technical mechanisms, rather than relying on vague, evocative language about probability clouds and quantum magic, ultimately serves the audience far better because it reveals genuine, checkable, falsifiable science rather than an impressionistic story that sounds compelling but cannot actually be verified against the published research literature. Every physicist and computer scientist working seriously in this field, from graduate students running their first small-scale quantum annealing experiments on simplified oscillator systems to senior researchers designing the next generation of error correction schemes, is engaged in exactly this kind of careful, incremental, checkable work, building toward a future where quantum computing's contribution to understanding chaotic gravitational systems, whatever form it ultimately takes, will be something the scientific community can point to with confidence, backed by reproducible results rather than by headlines alone. If there is a single thread worth carrying away from everything covered here, it is that the marriage between qubits and gravity, real and genuinely promising as it is, remains a courtship rather than a wedding, a relationship still being carefully negotiated through small experiments, patient mathematics, and honest, published uncertainty rather than a completed union already delivering dramatic answers. That is not a disappointing conclusion. It is, in its own way, a far more compelling one, because it means the most interesting chapters of this particular story, the chapters where quantum hardware finally scales past today's noisy limitations, where the first genuinely large-scale quantum simulation of a chaotic gravitational system gets published and independently verified, where astronomers first use a quantum-assisted search to catalog a previously unknown stable configuration among real observed star systems, have not been written yet. They are being written right now in laboratories cooling delicate qubits to fractions of a degree above absolute zero. In the careful back and forth of peer review that separates durable scientific progress from premature hype, and in the quiet, patient extension of a mathematical tradition that stretches back through Lorentz and Sundman, all the way to Newton's first triumphant solution of the far simpler to body problem more than 3 centuries ago. 3 stars, endlessly circling each other in a dance too intricate for any equation to fully capture in advance, remain exactly what they have always been, a genuine, humbling, and endlessly fascinating reminder that the universe still keeps some of its choreography a secret, and that figuring out how much of that secret we can responsibly, honestly, and rigorously uncover next is precisely what makes this one of the most exciting frontiers in physics today. So the next time you look up at a night sky full of stars that appear perfectly still and perfectly predictable, remember that a meaningful fraction of those distant points of light are quietly locked in exactly this kind of intricate, chaotic, gravitational negotiation, some settling comfortably into the stable, hierarchical rhythms that let a system like Alpha Centauri persist for billions of years, others still working through the violent, unpredictable churn that will eventually eject a member or trigger a merger, and all of them obeying the same set of deceptively simple gravitational equations that Poincare first showed could never be fully tamed by mathematics alone. Whether the next real breakthrough in understanding that hidden choreography comes from a more powerful classical supercomputer, a more cleverly trained machine learning model, or a genuinely mature, fault-tolerant quantum processor finally living up to its theoretical promise, the search itself continues, patiently, rigorously, and with the same sense of wonder that first drew a young French mathematician toward a prize problem about the stability of the heavens well over a century ago.